Thank you very much, guys. I'm going to take you from very high-level application and things to all the way to the bottom, the chip, which all applications run on computers. Computers need processor, and processor need a special functionality blocks that can enable them to do a special functions. For last 20 years, those innovations have been mostly missing. Thanks to AI, those innovations are required. We recognized that 3 years ago, working on another company with AI, and I'm going to present to you some really groundbreaking technology that is fit for AI computation, all the way to the bottom on the chip. I'm making a claim, standing in this venue. We want to be the #1 AI processor company in the world. Even with the thin audience, that should make a very serious statement. And we are enabling right now AI solutions, the smallest ingredient of it, being the processor, the chip, that can scale from very tiny device to a very large computer. And we have developed, we are demonstrating now the technology that will show you how that can be done. So a lot of people have discussed, there are a lot of papers in the world that have been published, that analog AI computing, if possible, if it can be made possible, can achieve very high performance in a very compact size at a very low power. Most of those papers will also conclude in the end that it is all great, but it is not doable, or it is not possible. We have made it possible. With past 2.5 years of research, we have made analog AI possible. Better yet, we have done it in such a way that it has all the strengths of digital technology. It scales in technology, it scales through process nodes, and it scales inside from very tiny device to a very large computer. And we are demonstrating that. We are also, we announced in November, last week of November, we announced we are doing the first chip, processor for on-device computing for extreme edge. And we are, the AI solutions that we are going to enable are very disruptive, again, at a very, at the chip level. We are building a processor. A lot of people talk about AI, and a lot of them know the usage. A lot of exciting usage have happened or emerging. But when you go down to the computing level, to the bones, to the wires, these are 3 components that are important. AI is different in computing. Everybody talks about it, and I'm sure most people know what that means. Arithmetic computation. In an AI computer, the arithmetic computation is a huge percentage. In a normal processor chip and an ASIC chip, arithmetic computation is around 3 to 5% of the total compute. In an AI chip, arithmetic computation is around 85 to 95% of the total computing. So very different in nature. And one needs to optimize. Yeah, it works. One needs to optimize the arithmetic computation without optimizing at the very basic level. Building a chip that can do very high performance at low power and in compact area, very difficult. We focus that, building on the arithmetic chips, on the arithmetic blocks. Other part, which is very important for every chip, is storage, called in SRAM, mostly SRAM or DRAM technology. We built our own storage to make AI computing more powerful. When I say more powerful, I mean all those 3 components: performance, low power, as well as compact size. The third item, which has been ignored for past 20 years, on-chip interconnect. All of you, if you work on chips, you know that in every generation, when we go to newer and newer technology, wires become slower and slower. And that's why a lot of companies, a lot of you, you work in the area, know that when we scale through the process, wires make the chip slower or actually completely, you don't gain anything in most of the cases. We worked on that. In case of AI, data sharing between cores or between different elements is a very, very large part of our consumption. We have optimized that to, we invented, for arithmetic, we have invented this analog AI processing capability with digital advantages. So we call it digital analog processing or digital analog technology. For storage, we have invented very specialized SRAM or the memories that cater to AI type compute load. And then low swing signaling. This is a groundbreaking innovation because this reduces the power consumption by a very, very large amount. Analog matrix computing, we talked a little bit about it. So far, people have been struggling to compute 8-bit accurately in analog. We are doing 32-bit accurate analog computing, 100% accuracy. This will give you the performance. This will also give you all of the advantages of digital because we can do very accurate AI, including even training. So we can represent very small numbers as well. And then this gives you the efficiency without any compromise. So we have broken the barriers or some of the limitations that analog research have faced in last 6-7 years since this whole concept came up. So we, for the first time, are showing you accurate, 100% accurate 32-bit, up to 32-bit analog AI computing. Low power SRAMs, you can see this in our lab. It is custom built for AI computing, and it's 300 to 500% more efficient than any such SRAMs or such memories that you can buy from off the shelf. So if you're an SoC designer or a chip designer, if you're going to go to a company and buy their SRAMs or the memory and the compiler, we have made it so efficient that you cannot compete with what we are building. This item we talked about, ignored for past 20 years, including big companies where we are standing here today. They have ignored this portion because, for whatever reason, people are not paying attention maybe. We have developed a technology that can provide 500%, actually it can be 1000% more efficient in carrying data from one core to other core. Powered with these three technology at the basic fundamental level, then we are building the architecture. I'm going to take you out to the architecture that naturally fits, or it is it actually computes the neural network as they should be computed. So if you look at it here, I'll just point it out. Lots of inputs, lot of neurons that need to be computed, and logically you compute layers and layers of neurons to compute any model. So we have built the architecture in such a way that you have an analog matrix computer. Every cycle you get a full layer of neurons as an output, and this can run at a very high frequency. So as an algorithm writer, you do not have to worry about how to compute every equation or every neuron. This core is able to compute a whole matrix and produce layers of neurons, and these cores can be ganged up together to compute as many neurons as you want in one cycle. So this is a very natural way to compute AI workload. So we have made an architecture that simply computes as a layer, as a neural model should compute. This, as we said, calculates entire layer every cycle, and it can be pipelined. There's another added advantage that it does not generate any intermediate variables. Since it does not, because all of the computing is actually happening in analog, you feed digital data, compute in analog, and get the output in digital. That means with the digital accuracy, that means the software person does not have to worry about or does not even know. As a matter of fact, even our RTL designers do not know that there is something analog inside. So that's how ingrained, that's how complete, and that's how embedded everything is. And each core can be configured separately, means each core can compute anywhere from 4-bit to 32-bit of weights as well as the input operands. And they can be configured independently. That means from software point of view, it's a very flexible engine. The way it is constructed, the way architecture is constructed, it will support all type of neural models, including the neural model. The neurons can evolve in every cycle. So you can change the model in every cycle using a very simple microcode that we have developed. So it has its own processor, a small processor inside. That means we can support what is being called as the future is the dynamic neural nets, where the model changes as the data or as the results change. Then, as we said, we can accept the core can accept operands 4-bit to 32-bit, and in every cycle you can change the width of the words, and you can segment each core to compute. I said 4-bit or 32-bit, but within the core itself, one neuron can be 4-bit, another neuron can be 32-bit computer. So extremely flexible, extremely programmable. Another part is character morphing, which is one of the big things because people talk about on-device inference, but on-device training so far at a very low power has not been possible. If you need to train something, send the data to the data center, and I think morning Oracle presentation was about how do you transfer the data to the data center, big trouble. Well, you can do on-device training here because the same device, same core can be doing inference using 4-bit, 8-bit, 16-bit, and can be doing training using far more accurate computing. We will be supporting floating point in next generation. So these numbers should tell you all. Compared to for always on functionality like wake up word, anomaly detection in industrial applications or healthcare applications, we are around 200x better than whatever is available MCU based today in the world, and around 2x to 3x better than the latest advancement that has been funded even by this company. So we are giving you the best performance in the lowest power consumption possible in the world today. And when we go to the edge cloud, some of these numbers I do want to draw your attention to. I am presenting the numbers that are real, Mac per picojoules. And this is what is possible in industry today, 0.2 to some people designing in 7 nanometer at 2.5 Mac per picojoule. Here is what we can achieve today in 40 nanometer 1 and 7 nanometer up to 10 Mac per picojoules. These are the tops with the biggest chip possible today, around 130 to 150, 350 tops. Some people claiming 350 tops. We were to build the same size chip, would be achieving around 1200. So peta compute in a small footprint in power consumption that you can cool the chip down with. It will not become a atomic furnace. Mac engines, instead of 130K in a large size chip, you can build 2 million to 4 million. I have not written the 4 million number. So obviously this type of technology is the next generation. I do personally believe that till quantum computing arrives, this will fill up the gap. And quantum computing, if it arrives, is quite a bit away. The last number here, very important, how much compute density you can pack. This is the 0.5, around teramax per second per millimeter square is the number that can be achieved in 7 nanometer, going to even 5 nanometer by very big companies. We can give you 8 to 12, okay, just to give you the scale. So power, performance, and compute density, all of them possible because of analog AI computing. The markets we address, pretty much we are starting with the I don't know, somehow it keeps going. We are starting with the on-device IoT market because we don't have any competition there. And then we'll be going slowly to vision, edge computing, and data center applications. We'll be building processors for all of these applications as the time goes by. We have taken our time. We have shown patience. We have been confident of our research, and now we will be reaping the reward. I don't want to spend too much time on this. On the left-hand side, you see the AI block. On the right-hand side is a normal ARM processor where you will write applications. So as a whole, from software point of view, so this becomes a complete processor and an SoC for on-device computing. This is our first product. And the software stack on the left-hand side to support the neural net is starting from TensorFlow, going down to our AI block, and on the right, simply an embedded or any operating system-based software that can be compiled using ARM infrastructure. We would be adopting other processors, the newer ones that are coming now, but this is our first product for now. I just want to give you some numbers. On-device computing for IoT, if you were to take one of the existing devices, you can do what is called on-device analytics, where you're doing always-on functionality, wake-up word, anomaly detection. You can take that chip. However, to work that chip, you do need an external MCU and an external ADC. And all these components combined, it becomes around 3 milliwatts of power, around in that range. When you use our chip, this is what you get, 80 microwatt. Everything integrated, connect the sensor, and so now very long time battery life without going to data center or without connecting anything. Our chip can power up on-device IoT, AI analytics. The power consumption is so low that now we are working on some projects to actually do energy harvesting, power the whole thing, so you would not need batteries. So batteryless electronics with AI functionality possible with this product that we are building right now. I do want to bring one more topic. That is the same graphic that I showed in previous slide. Is that whenever we go to connect an AI chip today, one needs a microcontroller or processor, which needs to be the master. The intelligence, artificial intelligence itself becomes slave. Right? Something else is master, intelligence is slave. Well, we are going to change that picture. AI will be the front runner first, connecting through our own ADC that we have built. And just to give you an example, if you go to take IP from outside industry, you'll get around 1 milliamp to 1.5 milliamp of analog to digital converter, which will connect to a sensor, which will then feed into an AI block or an MCU. Our analog to digital converter today consumes only 5 microwatt of power. This is our own development with a lot of research involved. So with this, we are able to make the analytics engine, the core of the AI computing as the master. Rest of the chip or the system in the background can be sleeping or completely powered down. Only when you detect something of importance, something of interest, you will wake up the rest of the system, including the built-in MCU inside for the edge devices. Status quo, we have a small chip. This chip is really small. I don't know if you can see it. It's very tiny. In a big board. It's on a development board. Actually, we built this board. You see a lot of paraphernalia here. We built it because we were thinking we will have to debug a lot of stuff. A lot of things can go wrong, so you can feed the power from here and there. It turned out within a few hours we found out that this was all useless because everything was working. So great work, great team. We have a fantastic team, I tell you. Because first time product built with all type of exotic technology, and the chip works within a few hours. So fully functional right now in lab. First time ever, 100% accurate analog matrix computing demonstrated, and we are now porting our applications onto this, so we'll have it in users' hands within no months, within no time, and people can't wait to get their hands on this. We just visited CES. We were thrilled to see that everybody came to our demonstration. Within minutes, they were not listening to us, what applications can be done. They all were coming up with their own applications. So tremendous traction, almost in all areas. Any areas you can think of, anywhere electronics can be present, AI can do things better. And we are finding it now where customers are saying, okay, this is how we want to do things. All public, large companies we are talking to right now. So very good. We are very glad to see the progress overall, and we have very good traction. And we are encouraged enough that we are starting actually a couple of projects to simultaneously take vision as well as the edge cloud computing market. So we are here now. We made this possible. I think this will come see us in our lab. You can see this happening today. With our engineering team, will be very glad to demonstrate. We are a startup company, so of course you have a business or something else to carry with you in our lab, that'll be wonderful. But otherwise also to quench your curiosity, please come by and contact us. Simple, straightforward. Thank you very much for your time. Questions?
Thank you for an excellent presentation. So for questions, please come out here. I was at an international HOC conference in panel discussion last year in Irvine. So the question posed to panel was that in the whole computing value chain, right, what happened is that anything like internet or something like that, the chip came and then basically semiconductors came and then their value, it became commoditized and then kind of their software took over of the value chain, right, 85%, 90%. So if the goal is for the hardware or the processor, could be processor, could be memory computing, anything, I'm just clubbing them together, to go to 30% of the value chain. Do you think AI or like new AI and ML can get us there, like make us not commoditized, but keep the innovations going so that we maintain a value chain of the whole computing? So do you think that this is a new, this has not become a repeat of the past where processor comes and then software takes the value chain, right? So is it something different this time?
I think AI, we are just beginning. We are just looking at I've been working on AI since 2012, just to let you know. After I left Sun, not Oracle. I think we are just beginning in AI as far, and the requirement, the characteristics, everything you look at how the AI gets computed is so different that one needs to think through the whole thing. The gone are, I think AI is different enough that it requires that you innovate all the way to the bottom of the food chain.
Thank you, excellent presentation. I'm also from ex-Sun, not Oracle.
Good.
One question is that, so I see this is more inference, not training, or training.
We are also going to be in training because we see the difference between training is inference with the feedback with the accuracy requirement. Since we do have the accuracy requirement and the core, every cycle can change its character. We will be doing on-device training and then later on in the training. Today we do not have any bottlenecks other than money.
And so, you had some excellent claim that you are this one. So even compared to Havana or Cerebras, you are, I know those are big fat chips, but you have the power advantage, but in terms of performance?
We will be far better because I showed you the compute density that we can achieve is actually 10 to 15, 20 times better than anything in the world today, even if they were in 7 or 5 nanometer. Today, when we compared one of the biggest company in the world doing very custom AI, they compared their compute density They themselves said that we are doing in 5 nanometer what you guys are doing in 40 nanometer. So it will give you all these items. Thank you.
Hi, a couple of quick questions. Could you share the dimensions of the AI engine, and also how balanced is the communication? So my understanding is that you compute a layer of the network, and then you can then communicate that to another engine while you load the engine with new data. So is that correct?
It's pipeline, right? If you worked on processor, all these things are happening a step at a time. One thing is doing one thing, other thing is doing its own thing. And this all happens as a pipeline, right?
So my question is does the compute have to wait for the communication, or does the communication have to wait for the computation?
No, that's the idea of the pipeline, that nothing has to wait for the previous or the later stage. So it is fully pipelined structure, where the core will be computing every cycle. In the next cycle, the data will be transferred to the next core. The next core will be computed.
Understood. And can you share the dimensions of the AI engine? In other words, so I guess the notion is the larger the engine, the more complex the computation, or how to think about it?
No, when you think about the AI, since we are able to compute a whole equation all in analog, in every cycle you are getting result of the entire matrix. Hence, using our engine, the computation, the bigger engine doesn't become more complex because you're computing new layers of neurons inside, so it's not even visible. So the algorithm becomes very simple. You just are manipulating the data going to the neurons, that's all. This is very different, as come by, sign our NDA, we'll explain you a little more detail. But this is really beautiful. We have taken our time, but what we are achieving here is definitely going to fill up the gap, I would repeat, till quantum computing comes.
My question is, how large of a layer can the engine take in one cycle?
How large means how many neurons computed? There is no limit, just number of cores.
No, I mean in one cycle.
Yes, in one cycle you can compute a huge.
Limited number of neurons.
Pardon?
I mean, just how many?
No. So each core can compute certain number of neurons. For the IoT 40 nanometer device, I'll disclose, each core can compute 8 neurons. But you can gang them up. Let's say we have 10 cores, so you can compute 80 neurons in cycle in this chip. If you put 1,000 cores together, you can calculate 8,000 neurons in each cycle. And it can be pipeline. And every cycle you can change. This core can be computing 8,000 neurons in one cycle. In next cycle, they all become serialized. One core is computing 10 neurons, another few cores are computing 20, 40, whatever number of neurons. So you can gang them up differently.
So I mean, if in the engine you fabricate many cores in the engine, and during the application, the size of each layer is smaller than what it can take. Does it mean that it wastes energy?
No, it's very well designed that way that actually every cycle you can power it down. Analog, when you compute, is such a small power. It's minuscule. It's less than the leakage of the chips. Just to let you know. Yes, sir.
I have a two-part question.
Can you please speak up? Sorry.
I have a two-part question. The first one is how does this architecture compete or compare with the GPUs that NVIDIA is providing in terms of the use cases and applications, especially around vision? That's one. And the second one is you mentioned a couple of times about quantum compute. So I just wanted your broader thoughts on one hand, AI is fairly data-driven and it's probabilistic. And quantum compute is also very probabilistic in its fundamental nature. And so AI and quantum compute seem to be made for each other in my opinion, but they are further down, as you said. So I'd just like to get your broader thoughts on that process.
Okay, so first question, NVIDIA, how does it compare with NVIDIA, right? GPU. GPU stands for what, do you know?
They were made for
Graphics processing, not AI processing unit, right?
Yes, but they're still the most valued AI processing.
Sure. Just because they happen to be there doesn't mean. I'm sorry, I'm making very controversial statement here, but graphics processing unit, the name tells you all. It's not an AI processing unit. As a matter of fact, in graphics, you have one pixel, you take it and proliferate into different type of pixel or many pixels. In AI, you have lots of pixels together and derive one information. It's upside down, if you ask me. The second question you said, quantum, we are hardware people. We leave the probability or how to choose the data, how to discard data to the software people. As far as the hardware is concerned, hardware should never be probabilistic, Otherwise, a lot of incidents in air happen, when the planes die. Hardware has to be accurate. That's why when we started, we are not making excuses. We are hardware people. We will compute accurately. Let the software application decide whether they want to take part of the data, they want to take full the data, or they want to discard it all, which is what AI does anyway. You compute a lot of stuff and then discard most of it, keep one, okay, this person or that person, right? So, yes, sir.
Is this engine geared specifically for AI, like a neural net, or can one think of this as a general purpose matrix manipulation?
You can think of it as a general purpose matrix or an equation calculator. As a matter of fact, we ourselves are finding, we did not think about it before, that we will be a DSP killer soon. Yes, sir.
You emphasize you have 100% accuracy with your analog AI devices. I'm just curious about how you achieve this 100% accuracy, since it's analog signals. There, if you have some fluctuation of the noise, it can easily break at 100% accuracy here. How do you achieve that?
Are you an analog designer?
I learned analog devices before. Yeah.
Look, I consider this as a very bad marketing. I mean, not good marketing to malign something. Very accurate analog computing has been done for ages, like 24-bit, right? In the communication, you look at, pardon that?
Then you will sacrifice the bandwidth and the performance and the speed.
We are not sacrificing. That's where the innovation comes, right? That's what we spent 3 years. Right? We have discarded hundreds of methods that could not work, and we finally found one that does do all the required things that is 100% accuracy with bandwidth, with the speed, with the compact size that we need. In our AI technology, we do not use any analog components. We only use transistors. Just wanted to disclose that. So it's all digitally, same digital technology, but doing analog stuff. That's what makes it special, because I don't have to go to the foundry to ask for a special process. If you're an analog designer, do not get discouraged by that kind of marketing, okay?
I can take one final question.
Hello, yeah, one quick question. Do you have some results on popular machine like bench?
We would have them very soon, sir. This chip just came back to life on 2nd January. When we learned, we rushed to CES. After that, we came here last night all the way till 12 o'clock. We were making these slides. We will have those results and we'll have it for you. Pardon? Pardon? We're porting these applications to the chip now. As I said, it just came to life in a couple of weeks ago. Not even a couple of weeks ago.
So thank you again, GP, for an excellent presentation.
Thank you, guys. Thank you.